Welcome. In this video, we are going to look at what main logical connectives are. We're going to translate English sentences into symbolic logic. We're going to go over what the scope of a logical connective is, or logical connectives, and we're going to go over truth conditions of logical connectives. Recall that a statement is a declarative sentence that can either be true or false. So here are some examples of declarative statements. However, in symbolic logic, we're not just concerned with the content of declarative sentences or what they say. We are primarily concerned with some of their main logical features. The main logical connectives we are concerned with include negation, which are usually expressed with phrases like is not, none, or no; conjunction, which are usually expressed with phrases like and, but, yet, also, or nevertheless; disjunction, which are usually expressed with phrases like or; conditionals, which are usually expressed with phrases like if then, only if, or unless. In sentential logic, we make a distinction between simple and complex logical sentences. A simple logical sentence is a sentence like Montreal is in Quebec or Boston is in Massachusetts. These are sentences that do not contain any of the main four logical connectives. On the other hand, a complex logical sentence is a logical sentence that does contain one of the main logical connectives. So for example, number one, Montreal is not in Quebec, is a complex logical sentence because it contains the logical phrase not. If Montreal is in Quebec, then Boston is in Massachusetts, this is also a complex logical sentence because it contains the logical phrases if then. This is a conditional sentence. Number three is a conjunctive sentence because it contains the logical phrase and number four is a disjunctive sentence because it contains the logical phrase or. So again, a simple sentence is a sentence that does not contain any logical connectives. So here are examples of simple sentences, and complex sentences are examples of sentences that do contain at least one main logical connective, like these four over here. So going back to our original examples, what I want you to do now is see if you can determine which of these are simple sentences or complex sentences according to what we just said. Please take a few minutes and pause the video now. Okay, welcome back. So if you said that A is not a complex logical sentence but a simple sentence, then you are correct because there are no logical connectives in A. 2 is a complex logical sentence because we see the logical phrase or here. C is also a complex logical sentence because we see if and then. D is also a complex logical sentence because we see the logical phrase and E is also a complex logical phrase because we see the logical phrase not. Now, in symbolic logic, every simple sentence can be translated to one of the main alphabet letters. And every complex sentence will have, at least, given that it has at least one logical connective, we symbolize the logical connectives with the following symbols here. So any negation will be symbolized with a tilde, and this is what a tilde is. Any conjunction will be symbolized with an ampersand. This is what an ampersand is. Any disjunction will be symbolized with a wedge. This is a wedge right here. And any conditional sentence will be symbolized with a horseshoe. We are also going to make use of parentheses and square brackets for punctuation in our translations of English sentences into symbolic logic, and we'll see how that works in a little bit. But for now, let us go back to our original examples. Montreal is in Quebec and Boston is in Massachusetts, to see how we symbolize these simple English sentences into symbolic logic. So whenever you have a simple sentence like this, you primarily symbolize the sentence by assigning to it one of the alphabet letters. So here we just chose P for Montreal is in Quebec and Q for Boston is in Massachusetts. So in symbolic logic, P just means Montreal is in Quebec and Q just means Boston is in Massachusetts. Now, one thing to note is that these alphabet letters are arbitrarily determined. So we could have picked any alphabet letter, but once we pick an alphabet letter, then we stick with that alphabet letter for our translation of the sentence into our symbolic language. Let's move on to complex sentences. So how do we translate the complex sentence, Montreal is not in Quebec? Well, since Montreal is in Quebec is just P, and this is a simple sentence, and Montreal is not in Quebec is a complex sentence, we merely symbolize this with not P, because P means Montreal is in Quebec, so wedge P, the negation of that is Montreal is not in Quebec. So Montreal is not in Quebec is symbolized into symbolic logic as not P. Let's go to a conditional statement. If Montreal is in Quebec, then Boston is in Massachusetts. Recall that Montreal is in Quebec is just P. Boston is in Massachusetts, it's Q. So if Montreal is in Quebec, then Boston is in Massachusetts is translated as if P horseshoe Q. What about Montreal is in Quebec and Boston is in Massachusetts? Well, again, we already know that Montreal is in Quebec is P, Boston is in Massachusetts Q. So we translate this into our symbolic language as P ampersand Q. So let's look at a more difficult case. So to consider the sentence, Tiffany and Ben sell jewelry or they sell beer. Now, this is a complex sentence because we have various instances of logical phrases like and or. So in order to translate this to its basic logical form in our logical language or symbolic language, we need to deconstruct this sentence to its basic or simple components. So what we do is we create a dictionary where we have sentences that represent the most fundamental or basic sentences that appear in this complex sentence. So here we have 4 basic or simple sentences. Tiffany sells jewelry, Ben sells jewelry, Tiffany sells beer, Ben sells beer. And now we try to translate this complex sentence into a complex symbolic sentence. So we start off with what's kind of obvious. Tiffany and Ben sell beer will be translated to T and B. Then we have an or here. So we put these parentheses here to indicate that this is a self-contained unit in a more complex sentence. Then we put our wedge here to represent or, and then what follows after that? Or they sell beer. Who's they? Well, Tiffany and Ben. We have these 2 simple sentences here. So what we write is A and C to represent they sell beer. So this complex sentence in English, Tiffany and Ben sell jewelry or they sell beer, is translated into symbolic logic as T and B or wedge A and C. Let's look at this more difficult example. So we have if gas goes up and wages don't, then people will take the bus or they won't go to work. So here we have a few instances of logical phrases. Again, the first thing to do is to create a dictionary by identifying the simple sentences within the complex sentence here. So here we have 4 simple sentences. I'll let you guys do that work. Once we determine what the simple sentences are, then we go back to our complex sentence and go step by step in translating it into our symbolic sentence. So what do we have here? We have an if-then statement, and within that if-then statement, we have a bunch of other logical connectives. So we know that we're going to have as our main connective, and I'll talk a little bit more about this in a second, is going to be the horseshoe, because this is a giant if-then statement. So if gas goes up, so if G and wages don't, well, wages will go up. That's a negation. So we do tilde W. We put parentheses around this to indicate that this is one component. Then what happens? Then people will take the bus. So people will take the bus, P, or wedge, they won't go to work, not A, or tilde A. So this complex sentence here can be translated into this symbolic complex sentence by taking those steps. Now, what is important in translating English sentences into sentences in our symbolic language is to identify not just the atomic or basic simple sentences, but also what the main logical connective is. So if we go back to this example, the main logical connective here is if then, and the way we know what the main logical connective is in a symbolic language is by looking at what is the main connective that the sentence is operating under. Well, in number one, this is simple because there is only one logical connective. What about number two? We see ampersand 2 times. Which of these is the main logical connective? Well, since this entire thing here indicated by the parentheses is taken as one whole unit, then what we have here is this ampersand, which I highlighted here, as the main logical connective. What about sentence 3? We have 3 logical connectives. Which is the main logical connective? Well, again, here we have one unit indicated by these parentheses here, but then that is encompassed by another unit indicated with these parentheses. So that tells us that the tilde here is the main logical connective because this has scope over this entire unit. For number 4, our main logical connective is the horseshoe because, again, following the previous steps, this entire thing is taken as one unit. So this is saying if all of this, then B, nothing else. There's no parentheses anywhere else. So we take this to be our main logical connective. And if you just kind of follow that logic, you'll see that for 5, this turns out to be our main logical connective because we take all of this, wrap it around with some parentheses, and now this is taken to be one unit, and so on. So I want you to look at these examples. I have underlined which of these are the main logical connectives. That will become important in understanding how truth tables work, but before we get there, we need to briefly understand what the truth conditions of these sentences look like. Well, consider a sentence not P. What's going to make a sentence not P true? Well, not P is going to be true under the conditions that P itself is false. P and Q is true when under the conditions that P is true, and in addition to that, Q is true. P or Q is true whenever P is true or Q is true, and if P then Q is true under the conditions that either P is false or Q is true. We can represent those truth conditions with the following truth tables. Take negation. We said that not P will be true whenever P is false, and also not P will be false whenever P is true. We said that P and Q will be true whenever both P and Q are both true. If either of them turns out to be false, or if both turn out to be false, then P and Q are always false. We said that P or Q is true whenever either P or Q is true. So here they're both true, this is true. Here P is true, Q is false, is both true. Here Q is true, P is false, is both true. So this is only going to be false whenever they both turn out to be false. And we said P horseshoe Q is going to be true whenever P is false or Q is true. And that occurs in all of these lines with the exception of the third line. The third line, what we have is P turns out to be true and Q turns out to be false. So the only thing that will make a horseshoe statement false is whenever the thing that comes before the horseshoe is true and the letter that comes out after the horseshoe is false. Any other combination will make a horseshoe statement true. Now, when it comes to conditional statements or horseshoe statements, that may sound a little bit weird, but if we take a little time to look and reflect on the way we use conditional statements, we'll see that it actually isn't that weird. Consider the statement, if it is raining, then wear a jacket. Imagine your mom says that. Under which of these scenarios would you be disobeying your mom? Well, consider scenario number 1. If it is raining and Bob wears a jacket, or you wear a jacket, right? Then this entire statement is still true because the conditions laid out by your mom have not been violated. If it is not raining and Bob is not wearing a jacket, let's assume it's a sunny day, then this is still true because the conditions have not been violated. Take scenario number 3. If it is not raining, but Bob does wear a jacket, if this is false and this is true, well, this is still true, the entire sentence is still true because the conditions have not been violated. Now let's look at scenario number 4. if it is raining and Bob does not wear a jacket, meaning if this turns out to be true and this turns out to be false, that is the only situation in which this entire thing is false because the conditions of the statement have been violated. And that is how conditional statements work. That is why true